Okay, so we're going to explore a bit how CPUs and GPUs handle computational tasks differently in terms of performance for specific things or methods or algorithms that are preferred in machine learning. What we're going to do today is try to estimate the area of an ellipse without using the well-known formula of the area of an ellipse, just with the knowledge of the equation that describes the ellipse's, let's call it edge. Okay, so this is ideal, perfect to illustrate the difference between CPU and GPU and why we use GPU so much in machine learning. So I have two implementations that are extremely similar in two different Jupyter notebooks. And we're going to look at the first one. And the first one is done in NumPy. So we're going to essentially be throwing darts at a rectangle. And here it's 800 darts at a rectangle that is 4 wide and 2 high. We're going to do the exercise repeated 20 times, and so that we can come up with several estimates of the area and average them and get an idea of the accuracy that we have. By the way, since the area is equals to pi times the major radii and the minor radii, in this case this would be pi times 2 times 1. This is equal to 6.2831. So we're looking for this number to be calculated. So this is our formula for the ellipse, and it's x minus the center, and this is going to be centered around 2x and 1y. This is half the rectangle width. So just so you see it, the ellipse is going to be, see, this is the ellipse. It's going to be on 2, 1. So it's going to be all in the first quadrant. It's going to be between 0 and 4 in the x-axis and between 0 and 2 in the y-axis. So this formula represents where the ellipse is. And this formula is going to give us a result when we plug in different values for x and y. And the result is going to be between 0 and 1 for points that are, or darts, that are inside the ellipse. Exactly 1 for darts that are exactly on the ellipse, on the contour or edge of the shape, and more than 1 for anything that's outside the ellipse. So we're going to time this, initialize a random number generator, and we're going to generate 800 samples, and we're going to scale them by the width and height. So basically, these are the x and y coordinates of each of our darts. And we're going to calculate or plug them in, sieve each dart through the ellipse formula. Then we're going to check which ones are inside and which ones are outside, and which ones are roughly on the edge of the ellipse, within, plus minus 0.01. And we're going to count how many points we have inside the ellipse. I'm going to comment out this to make it fair. And we know that we're going to be throwing 800 darts. So the ratio of those that are inside divided by those that are outside multiplied by the rectangle area is the approximated area that we're evaluating. We'll save the areas for later, and then after the calculation ends, we're going to plot it and display the approximated areas, calculate the mean, the standard deviation, standard error, and variance. So let's run this. So this is going to take a few seconds to do the whole thing, but about 15 seconds more or less. So if we did 800 samples, 20 epochs, we're processing or throwing about 16,000 darts. So the CPU was able to do the pure calculation in 13.5 seconds. And this is a plot of the last of the 20 runs. And you can see the darts that fell inside, the ones that fell outside, and a few green ones that have fell just on the edge of the ellipse. So we're getting an average of 6.25, and we're getting plenty of standard deviation and standard error. Now, let's look at the same code, or almost the same code, but we're going to be using PyTorch. And what PyTorch is going to allow us to do is to choose whether we want to run this on CPU or on GPU. And we're going to straight up send it to GPU. So we're going to use 1.6 million samples. Okay? So instead of 800, 1.6 million. And instead of just 20 epochs, 20 repeats of the experiment, we're going to do 1,000. The rest of it, basically the same. The formula here is a bit more readable. We're going to also compile this so that it runs entirely on the GPU. We're using the same seed, although the numbers are not going to be exactly alike, and we're forcing it to run on GPU if the GPU is available. And again, collecting or generating random numbers this is always between 0 and 1. That's why we multiply by the width and height so that we're sending all our darts in the right area. We're sieving those darts through the ellipse function, and then figuring out which ones are inside, outside, and so forth. And I think I commented out this one on the prior one, but I'm going to just leave it. So this would be the sum of, or the count of the numbers that are going to, the count of the darts that are inside the ellipse, and the same approximate area formula. And we're going to just, store them, keep them for later. And after that, we're going to copy we're timing just a pure calculation. Then we're sending this 1.6 million samples from the GPU into the CPU so that we can plot it. Okay, let's run it. So this is running, this is running, this is running. And the whole calculation was done on the GPU in 1.296 seconds. And there are so many darts being thrown, you can barely see that they're dots. Well, actually, you cannot. And the number we were looking for is here. Wait, 4 or 5 decimals of precision, very little standard deviation, standard error that's really, really very low, and the same for the variance. This is the difference. So we did 1.6 billion darts in total versus 16,000 in the other. So quick calculation. $1.6 billion divided by 16,000. So we did 100,000 more. So to be able to run the same experiment we run in the GPU in 1.2 seconds, we have here to do 13 times, let's say 13.495 times 100,000. That's 1,000,000 seconds. That's 22,000 minutes. That's 374 hours. That's 15.5 days versus 1.3 seconds. Just so you realize that I'm not lying about this, let's try to make something with 16,000 samples. Still 20 times more than in the prior example. And you can see the dots here. They're much, much more than here. And you see the slight loss of precision there. Still, standard error, variance, standard deviation, very low compared to CPU because the sheer amount of extra numbers. And it took almost no time at all. And the other thing to notice here is that I basically dropped the complexity by a factor of 2, right? It's 100 times less data. It roughly still takes the same amount of time because of the GPU's boundless parallel computer power. So let's bring this up. So that's CPU versus GPU. Hopefully that helps. And I'll see you back on the next video.